All right. So the outcomes for today. Um, we are continuing with using compounds and chemical formulas. So last week we were looking at how to name them and how to identify a covalent versus an ionic. So remember, when you're dealing with a covalent compound, you're looking for two elements that are non-metals for a covalent. And then for ionic, you're looking for one that has a metal and a non-metal. So make sure you're paying attention and looking at that because the naming rules are different for both of those. Remember, if you see a Roman numeral in the name, that tells us it's transition metal. That Roman numeral tells us the charge of the transition metal. And then the reverse of that is if you're looking at a formula and see it's a transition metal or lead, bismuth, tin, or antimony, SN, SB, PB, BI, all of those will be treated like transition metals as well, even though they're not technically in that list. Today's the chapter that we're going to today, or the chapter that we're starting now, is going to be chapter 6. And so now we're going to start kind of putting numbers to these formulas. So we're going to be looking at something called molar mass today. Sometimes it's called formula weight. Just a second. All right. So today we're going to be looking at formula mass or molar mass. Sometimes it's called formula weight. Distinguish between those, how to use the chemical formula to determine that. We're going to be calculating the number of ions or atoms in 1 mole of a compound or in 2 moles of a compound, things like that. So we will identify what a mole is today as well. And then hopefully we will get to the part where we're starting to look at percent composition. When we look at the molar mass of a compound and compare it to the individual elements in there, we can determine what percentage of each element is in that compound. The math that we're going to be doing today is fairly straightforward, simple math. So it's not going to be anything overly taxing. The only one that might give you a little bit of pause is when we're calculating the number of atoms in there, and it's because we're going to be using a scientific notation number. All right, but we have to just understand what it's for and what it's telling us. All right, so when we look at a chemical formula, it gives us certain information. Chemical formula, recall, tells us the elements that are present in a compound. So if I'm looking at, let me do this. All right, so if I'm looking at the compound calcium chloride, that tells me certain things about that compound. I know that I have calcium. I know that I have chlorine in it. I also know something about how many of each it tells me. It tells me the relative number of atoms of each of the atoms or ions present in the compound. So how many calcium ions are in this compound as it's written? 1. How many chlorine ions? 2. So it's a ratio of 2 chlorines to 1 calcium. All right. And the reason why I'm referring to them as ions and not atoms is because this is an ionic compound. Ionic compounds are always between a positive and negative ion. All right. Chemical formulas allow chemists to calculate a number of other characteristic values for a compound. So it lets us determine some things. And one of the things, and one of the focus for today, is it allows us to calculate something called formula weight or molar mass. These two, formula weight and molar mass, numerically are going to be the same thing. They're based off the atomic mass off the periodic table. All right. The only difference is formula weight will be measured in AMU, whereas molar mass is in a unit called grams per mole. All right. We will use molar mass pretty much from this point on in the class. Just about every calculation that we're going to do from this point on was going to require us to get a molar mass in some form or shape. So we're going to have to understand what's happening there. All right. So just kind of leading into this, if I'm looking at the formula CaCl2 as it's written, what would be, in terms of mass, what would calcium's contribution be to this formula? So what's calcium's mass? All right, so let's go with 1 decimal place on it. So when I'm looking at calcium, it's 40.078. So I'm going to say 40.1. All right. So calcium is contributing 40.1 AMU or 40.1 grams per mole. What's chlorine's contribution going to be? Just 35.5? 2 times 35.5, right? Because it's 2 chlorines in it, so 71-ish. All right. So that's what we're kind of looking at. So to get the molar mass of this, I'm going to add that together. All right. So I'm going to show it to you in a little bit more step by step. I just wanted to get you to start thinking about what we're doing today. All right. So the molar mass of a substance, is equal to the mass in grams of 1 mole of the substance. And so the molar mass of a substance is equal to the mass in 1 mole of a substance. So if I go back to my calcium chloride, where I said that calcium contributes 40.1, and then chlorine, we said it contributes 2 times 35.5. So we'll say that's 71.0. I'm going to maintain that 1 decimal place. All right. So I go 40.1 plus 71.0. And that gives me a molar mass of 111.6 40.1, and that's grams for every 1 mole of CaCl2. So if I had 2 moles of that, I would double that mass. If I had 3 moles of it, I would triple that mass, and so on. All right. And that's what it's kind of telling us. All right. So the second statement, and I mentioned this earlier, you'll hear this referred to different ways. Sometimes you'll see the question asked for molar mass. Sometimes you'll see the question asked for formula weight. But the molar mass and formula weight of a substance are numerically the same. The numbers are the same amount. All right. The difference is, so if we're looking at calcium we can say is 40.08 grams per mole. Can you write your score on the top? So if I was asking for the molar mass of pure calcium, I would say it's 40.08 grams per mole, or 40.1 grams per mole. If I was asking for the formula weight for it, I would say it's 40.08 AMU, atomic mass units. So the mass of it, formula weight or molar mass, is equal to the average atomic mass of the element. So we're going to use the periodic table. Now, in my example and in the practice that we did today, that we're going to do today, I'm only asking you to go to 1 decimal place. Most of the time, the best practice is to go to 2 decimal places, because that'll give us the best numbers overall. All right. So when we're pulling the average atomic mass, 2 decimal places is a good standard to use. I'm doing it to 1 just for easier math today, or less math. All right. So the molar mass of a compound is calculated by adding the masses of the elements present in 1 mole of the compound, or 1 mole of the molecules or formula units that make up the compound. So remember, a molecule or a formula unit is just this represents a formula unit of CaCl2. All right. That's what we're looking at. All right. If I ask for the molar mass of an individual element, it's just the average atomic mass. But if it's in a compound, we have to see if there's any subscripts, and then we'll multiply those subscripts and things like that. Thank you. No, I don't need it back. All right. Did everybody have what they need off of that one? Sorry. All right. So all right. So when we're looking at, we're going to be looking at water. So 1 mole of water molecules contains exactly 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So what does that statement mean as far as putting this in a chemical formula? What is the chemical formula for water? All right. So if I have 2 moles of hydrogen atoms, that's the H2. 1 mole of oxygen atoms, that's just shown as the 1. All right. So if I asked us to calculate if I asked us to calculate the molar mass of water, let's go ahead and look at how we would approach this. So the 2 elements that I have involved are hydrogen and oxygen. So what is the mass of hydrogen? And let's go with 2 decimal places this time. What's the mass of hydrogen off the periodic table? What is the mass of hydrogen off the periodic table? 1.01. All right, so I have two hydrogens, and their mass is 1.01. So that means hydrogen's contributing 2.20 or 2.02 grams to this equation. I have one oxygen. What's the mass of oxygen to 2 decimal places? 16.00. All right, and so what would the molar mass of water be? All right, so the molar mass of water in this case is going to be 18.02 grams per mole. All right, which is what the book tells us. All right, and so all we do is look at the masses of each element involved. So if it has a subscript, we're going to multiply the mass by that subscript, and then we add those two together. So calculating molar mass is not complicated, but it's a skill that everything from this point on just kind of bases off of. All right, so this third time I'm going to make this statement, but remember, if it asked for formula mass or formula weight, numerically, molar mass and formula weight are calculated the same way. The only difference is the units that you're going to write. So we're typically going to use molar mass, which is grams per mole. But if it asks for formula mass or formula weight, we would say atomic mass unit. All right. All right. So based off of what we just did, I would like for you to go ahead and calculate the molar mass of barium nitrate. so everybody can see it over here. All right. So setting this up, we have one barium in this compound, and that's going to be 1. So we have 1. We look up the atomic mass of barium. It's 137.33. Nitrogen, we have 2 nitrogens. Each nitrogen is 14.01. So 2 times 14.01 gives me 28.02. And then I have 6 oxygens because I have 3 oxygens in the nitrate and I have 2 nitrates there. So 6 times 16 gives me 96. So what atomic mass do we come up with for barium nitrate? (261.35 grams per mole). So for every 1 mole of barium nitrate, I'm going to have a mass of 261.35. All right. Now, everything on the periodic table is based off of carbon. All right. So if we look at carbon, just carbon by itself, what would the mass of 1 mole of carbon be? (12.01 grams). So the mass of 1 mole of carbon is 12.01. What would the mass of 1 mole of oxygen be? 16. What would the mass of 1 mole of aluminum be? 26.98. All right, so we are looking at, when we look at this, we're just looking at the average atomic mass off the periodic table and looking at how many that we have. And it's all based off of looking at it in terms of 1 mole. Now, so the next thing that we're going to have to describe, is what is a mole. So 1 mole of carbon is 12.01 grams, but that also tells us a certain number of atoms. So 1 mole of carbon also represents 6.022 times 10 to the 23rd atoms of carbon. We can go from moles to mass, and we can go from moles to atoms, but we can't go from mass to atoms. So we always have to go back to moles first. So a better way for me to write this is 12.01 grams of carbon equals 1 mole of carbon, which equals 6.022 times 10 to the 23rd atoms of carbon. Do you just know that, or is there some way we can get that? So That is something called Avogadro's number. That is a number that we kind of have to memorize, but it's also in our packet. So every element. So 1 mole of any element is always 6.022 times 10 to the 23rd atoms. All right. And so the next slide that I'm going to pull up talks about this. So 1 mole of a substance is equal to 6.022 times 10 to the 23rd. And when we talk about this number, it can represent particles, atoms, ions, formula units, molecules, any of those things. It just depends on how the question is phrased. All right, so when we look at this, and again, this is called Avogadro's number. All right, and so we can put this in context of any, we can put this in the context of any compound. All right, so if I go back to my example that I used earlier, calcium chloride, and I wanted to know how many atoms or how many ions, calcium ions, are in 1 mole of CaCl2. So in 1 mole of CaCl2, I have 1 mole of calcium ions. So that means that I have 6.022 times 10 to the 23rd calcium ions. The way that I got there is 1 mole of calcium ions times this number gives me that number. All right, so 1 times anything is that number exactly. Now, chlorine, I have 2 chlorines in it. So if I ask for how many ions, how many chlorine ions in CaCl2, so in CaCl2, I have 2 moles of chlorine. So 2 moles of chlorine times 6.022 times 10 to the 23rd gives me 1.204 times 10 to the 24th. Or if you just did the math directly, you would get which is the same number, but I would rather it in the correct format for scientific notation. So that's why I moved the decimal 1 more place. All right. So does it make sense as to what I've done here? All right. So let's look at this and let's make an attempt on this. All right, so go ahead, try this on your own, and then I'll go over the answers in just a minute. So it says, how many atoms of nitrogen in one mole of the molecule N2O4? So the first thing that I have to figure out, in 1 mole of N2O4, or in 1 mole of dinitrogen tetraoxide, how many moles of nitrogen are in that? So I have a subscript of 2 right there, so I have 2 mole of nitrogen. Now, to figure out how many atoms of that, what am I going to have to do? I'm going to take my 2 mole of N times so what's 2 times 6.022 times 10 to the 23rd? 2 times 6 is 12. So it's 12.044 times 10 to the 23rd, or rewriting it in a better format, 1.204 10 to the 24th. All right, go ahead and do it for oxygen based off of what we just did. All right. So when I do this one, when I look at this one, we're going to say 4 mole of oxygen times Avogadro's number. And I get 2.409, maintaining 4 sig figs. Any questions? No, I'm not asking for the total number of atoms. Now, if it asked for the total number of atoms, yeah, you could add them together. But it didn't ask for it in this case. Now, if it just asked for how many molecules of N2O4 we have in 1 mole, then it's just Avogadro's number. Because if it's 1 mole, it's just whatever it is. If it was 4 moles of N2O4, then we could do that. All right. So go ahead, see if you can figure out this one based off of what we've just done. So how many atoms are in 5.8 moles of helium? All right. So which answer choice is going to be our best answer choice for that? D. because 5.80 times 6.022 gives us 34.9, and so we can shift it 30.49 times 10 to the 24th. All right, questions on that? All right. Now, the other concept that we're covering today is percent composition. Percent composition is it's basically the percent by mass of each element in a compound. So in this, when we're doing percent composition, if we're not given a mass of the compound, we can assume that we're dealing with like 100 grams of the compound or something like that, but we're always going to use formula mass. So let's kind of look at this in terms of how we would set this up and all of that. So the percent composition is the percentage by mass of each element in a compound. All right. The percentage of an element in a compound is the same regardless of the sample size of the compound. So the nice thing of dealing with percents is we're always going to get the same number no matter how big or small the compound is. So like when I report data for my classes and all of that, I report it by percentages, not by number of students, because I can compare this class has 19, whereas my third block has 29. So, but I can look at, okay, 3% scored this and 3% scored that, and to see if we're following track-wise. All right. So here is the ultimate formula for doing this. So when we look at a chemical formula, we're going to take the mass of that element in 1 mole of the compound divided by the molar mass of the compound. So example I'm going to use is I'm going to go back to my barium nitrate from earlier, and I want to know what percentage barium is. I want to know what percent of barium is in that compound. So earlier we found out that that barium nitrate had a molar mass of 261.35, right? That's what 1 mole of barium nitrate is. So if I wanted to figure out what my percent of barium is, I would take that I have 1 mole of barium in 1 mole of barium nitrate, so I have 137.33 divided by 261.35 times 100. So what is my percent of barium in this compound? Yeah, so let's preserve. So let's go ahead for the percentage. Technically, we'd want to preserve 5 sig figs in our answer for our percentage, because I have 5 sig figs divided by 5 sig figs. So I could say that it's 52.546. Or we could say, if we wanted to go by the nearest whole number percent, we could say 53%, 52.5%, something along those lines, but we would see that. Now, if I was looking at it for nitrogen in this case, so this is that's for barium, disregard the little mark right there. That's percent barium. if I was looking for percent of nitrogen, still going to be out of the total mass of it, but what number am I going to put on the top position there? How many nitrogens do I have in there, and then what's the mass of nitrogen? So I have 2 nitrogens in this compound. Nitrogen's mass for 1 is 14.01, so 28.02. And so I could find out all right, and so in this one, I preserve 4 sig figs, and I would say that I have 10.72%. Now, do I have to do that calculation to find out my percent of oxygen? Or what's another way that I could do this? If I add those two together, subtract from 100, that gives me the percent of the other element in there. So, or we could do it the other way, and we should get the same number. That's a good way of checking when you do it and all of that. All right, so percent composition is simply that, and it's fairly straightforward of how we do that. And so we just really need to know that formula to be able to do it. All right. So if I gave you a question like this that said, calculate the percent composition by mass of each element in magnesium nitride, what's the first thing that we're going to have to figure out? I heard somebody say it. The formula. All right. So what's the symbol for magnesium? What's the symbol for nitride? It's N. So I need to know that magnesium forms a +2 and nitrogen is a -3. So what's the formula going to be for this? Now, what's the next step that I need to do? I need to get the molar mass of it, right? So I have magnesium and I have nitrogen in this. I have 3 magnesiums. I look up magnesium's mass on the periodic table. It is 24.31. And then I have 2 nitrogens, 14.01. So we find out we have a molar mass of 100.95. And then now I can do my percent by mass. So go ahead, calculate the percent by mass of magnesium and the percent by mass of nitrogen.
Excuse me, Mr. Martin?
Yes.
Trace Brashear?
Yes, I do.
Who's with us in office to get checked out?
Yes, ma'am.
Thank you.
Hold on. Trace. Yeah. It's just molar mass. Yes, please. All right. So what do we get for the percentage of magnesium? So magnesium percentage is 72.24. What do we get for the percentage of nitrogen? I get 27.76 because I had to round that. So there was two ways that we could approach that. We could have just went 100 minus 72.24 and got it, or we could have done 28.02 divided by 100 divided by 100.95 and then multiplied there. All right, questions about doing this? All right, so for the most part, this is really straightforward stuff. I'm going to get more into percent composition as we progress in this unit because we'll continue using that. We will get more into the Avogadro's number and those things as we progress into this as well. So let me pass this out and I'll kind of talk about the last part of this. 1, 2, 3, 4, 5. Take one, pass it back, please. Take one, pass it back, please. Take one, pass it back, please. All right. All right. So I'm going to look at this sheet real quick, just kind of making sure that we understand what I'm asking for on it and all of that, making sure that we are all on the same page. So if we look at the example, and we did barium nitrate earlier, except for we did it to 2 decimal places instead of 1. Notice in this instruction, I'm asking us to calculate the molar mass of the following compounds in grams per mole, round all atomic masses to the nearest 0.1 gram per mole. So everything should be in tenths. All right, so when we look up the 3, we get, there's 1 barium in there, there's 2 nitrogens, and then there's 6 oxygens. So 137.3 plus 28 plus 96 gives me 261.3. All right, now that's how we would do it for this one. Now notice here, I didn't give you the formula, I gave you a name. So what's the first thing that I have to do here? Carbon dioxide, I have to figure out what my formula is, right? So I'm going to go CO2. All right, so now I know that I have 1 atom of carbon and I have 2 atoms of oxygen. I look up carbon off my periodic table. Carbon is 12.01, so at 1 decimal place is going to be 12.0. Oxygen is 15.998 or 999, so 1 decimal place is going to be 16.0. So that's contributing 12.0. That's contributing 32.0. I add them together. And so for carbon dioxide, I get a molar mass of 44.0. All right, so for the remainder of time today, I want you to go ahead. want you to go ahead, calculate the molar mass of each of these. There's that one. So for the last two, I just didn't draw in the little grid lines. If you want to use the grid lines, great. If you don't want to use them, that's fine as well. And then that last box is just an extra box. Don't worry about that. But go ahead, finish this sheet. If you're not finished Chapter 5 active, you need to do Chapter 5 active. That is going to be closing up soon. I think it closes up sometime tomorrow. So make sure you get that done so that we can continue to have our active grades become relatively high. All right.